Hi there. In this video, we're going to continue our survey of descriptive chemistry with a look at oxidation-reduction reactions. In an oxidation-reduction reaction, one or more electrons are transferred from one chemical species to another. So, for example, iron oxide, Fe2O3, can react with 3/2 of a mole of solid carbon to form 2 moles of solid iron and 3/2 mole of carbon dioxide gas. This is a process that occurs in blast furnaces and is involved in the smelting of iron ore. And in this reaction, there's several things that are going on. We've got carbon is being converted to carbon dioxide. That process is called oxidation, and it's fairly clear, I think, why this is called oxidation. The carbon is combining with oxygen to form carbon dioxide. The iron ore, the Fe2O3, in this process is being converted into solid iron, and this process is called reduction. Now, the use of the term reduction for this process may not be obvious, but the origin of this is in the history of metal smelting. Processes like this were very common, and if you imagine starting with a large quantity of iron ore and reacting with solid carbon and ending up with the pure iron, going from Fe2O3 to just Fe, all of those oxygen atoms are going away. They're leaving with the carbon dioxide, and so the solid that you've got going from the iron ore to the pure iron, the metal sample gets smaller and lighter, and so the metal appears to be reduced, and that's why a process like this is called reduction. Now, the terms oxidation and reduction have been, their use has been broadened beyond ore smelting contexts, and another example of an oxidation-reduction reaction is the reaction between solid zinc and aqueous copper sulfate, which forms aqueous zinc sulfate and solid copper. In this reaction, the zinc is being oxidized to zinc sulfate, and the copper sulfate is being reduced to copper. And I want to look at this reaction a little more closely to see exactly what is going on. And in particular, I want to see if we can figure out where this electron transfer is coming into play. So here's our reaction. I'm going to spread things out to give myself a little more space. And so looking first at the oxidation part of the picture, the zinc is starting out as just solid zinc, the pure element, and it's being converted to zinc sulfate solution. And as we've seen, aqueous solutions of ionic compounds like this are separated into ions, and so the aqueous zinc sulfate is a mixture of zinc 2+ ions and sulfate ions in water. So this is our oxidation. And then on the reduction side of things, copper sulfate is another ionic compound dissolved in water, and so it is copper 2+ ions and sulfate ions dissolved in water. And that copper is being converted into solid copper metal. So in this reaction, you're starting off with a chunk of solid zinc metal that's surrounded by a solution of copper sulfate dissolved in water. And so zinc is sort of a silvery solid metal. Copper sulfate solution, and specifically the copper 2+ ions, form a pretty blue solution. And then that's what we're starting with in this reaction. And then as the reaction proceeds, the zinc metal is being converted into zinc ions, and the copper ions are being converted into copper metal. And so what you end up with is all of the zinc has dissolved and formed a colorless solution, and all of the copper has come out of solution and formed a solid mass of copper metal. So this is the reaction, and if you look at each of the two processes, the oxidation and reduction, in the oxidation process, zinc metal is being converted to zinc 2 plus ions. And so you can see that in order for that to happen, electrons need to be removed from those zinc atoms. Zinc is starting out being neutral, and it's ending up as a +2 ion. So 2 electrons had to be taken away from each of those zinc atoms. And we can represent that schematically like this. We can say zinc, solid zinc is being converted to zinc 2 plus ions, and then 2 electrons have been removed. This would be the oxidation part of this reaction. Similarly, in the reduction part of the reaction, we've got copper 2 plus ions that are being converted to copper metal. And in order for this to happen, those copper 2 plus ions have to be gaining a pair of electrons to form neutral copper atoms. And so we can schematically represent the reduction part of the picture as copper 2 plus gaining 2 electrons to form neutral atoms of copper metal. So, and this is typical of oxidation and reduction processes. In an oxidation process, electrons are removed from a chemical substance. In a reduction process, electrons are gained by a chemical substance. And one way to remember this is through the mnemonic oil rig, which stands for oxidation is loss, reduction is gain. So in an oxidation process, there's loss of electrons. In a reduction process, there's a gain of electrons. Now, this notion of separate oxidation and reduction processes is a useful idea, but it's more than that. It's actually, you really can separate the oxidation from the reduction. And for example, you could imagine splitting up the solid zinc from the solution of copper ions into 2 separate beakers, and then forming and then having the reaction proceed, and you can make the reaction go by connecting the compartment with zinc with a wire to the compartment containing copper. And then if we complete the circuit using something called a salt bridge, then this allows us to physically separate the oxidation part of this reaction from the reduction part. On the left, the zinc will dissolve to form zinc 2 plus in solution, and on the right, copper 2 plus will gain electrons to form copper metal. And in order for this to occur, electrons have to leave the zinc compartment and flow into the copper compartment. And so by setting up separate compartments for the oxidation and reduction, we can force electrons to flow through a wire. And this is exactly how things like batteries and fuel cells work. They physically separate an oxidation process from a reduction process and force electrons to go through an external wire. So let's take a look at how these ideas apply to the smelting of iron ore. So in this reaction, we said that the iron oxide is being reduced to iron metal, and the copper is being oxidized to carbon. I'm sorry, the carbon is being oxidized to carbon dioxide. And if we look at this a little more closely, iron oxide is an ionic compound. It is made up of iron ions and oxygen ions, And in this particular compound, those ions are Fe3+ and O2-. There's 2 of the iron ions, 3 of the oxygen ions, and so altogether the charges cancel out, and it's a neutral compound overall. But you can see that the iron is starting out as a 3+ ion, and it's ending up as a neutral atom of iron metal. And so the iron is gaining electrons in this reduction. In the oxidation, we're starting with just solid carbon, so we've got neutral carbon atoms, and we're forming carbon dioxide. Now, we just finished saying that in an oxidation process, electrons are lost, and so the carbon atoms are somehow losing electrons, but we're not forming ions here. Carbon dioxide is not an ionic compound, it's a molecular compound. And so the carbon is not forming ions, but we could imagine if that carbon dioxide, if that were an ionic compound, oxygen normally forms ions with a charge of 2-, and so if this compound were ionic, then the carbon would be existing as an ion with a charge of 4+. In this way, CO2 would be a neutral compound overall. And so if we look at it as this sort of hypothetical ionic version of carbon dioxide, then we can see how electrons are being lost from the carbon to form this hypothetical carbon 4+. So again, if carbon dioxide were ionic, the carbon atom would have a 4+ charge, and this 4+ is called the oxidation number of carbon, and it's represented as +4. So with charges, we put the number before the sign. With oxidation numbers, we put the sign before the number. And that pattern is there just to help distinguish between charges and oxidation numbers. Certainly they are related ideas, but they are different things. And so to help avoid confusion, with charges, we put the number first. With oxidation numbers, we put the sign first. So we can keep track of oxidation and reduction processes by looking at oxidation numbers of atoms in a reaction.